Welcome to Module 14, Digital Video and Video Coding. So in this module, we will discuss how digital videos are created, sampled, and compressed, focusing on the techniques that makes modern video format efficient and practical. Let's talk first about what a digital video is. Digital video leverages the human eye's ability to perceive a rapid sequence of static images as continuous motion. This phenomenon is called the optical illusion of movement. A digital video is essentially a sequence of images or frame played at high speed. For smooth motion, the frame rate measured in frame per second, FPS, should be at least 20 FPS. From the mathematical point of view, a video is a signal that varies in three dimensions, 2D for the space and 1D for the time. We can see it in the picture. Let's do an example related to the quality connected to the FPS. So here you can see the same video in 4 different versions with using 4 different frame rates. The first is at 5 FPS, the second 15 FPS, the third 30 FPS, and the last is 120 FPS. So you can notice that the one at 5 FPS has motion that looks really choppy. The one at 15 FPS seems a bit snappy, even if it shows a certain fluidity. The one at 30 FPS, the movement appears very smooth. And lastly, the one at 120 FPS, there is no perceivable differences with respect to the one with 30 FPS. This is due to the fact that at 20 to 30 FPS, our vision system already perceives motion at the maximum of fluidity. So, however, recording at higher frame rates can be useful for video manipulation. So for instance, the video that you can see here has been recorded using high-speed camera at 1 million FPS. Using such a high frame rate permits to slow down the video by 8,000 times, creating a very fluid slow motion effect that wouldn't be possible anyway. So the frame rate directly affects how we perceive motion fluidity. Higher frame rates provide smoother motion, but they require more computational resources and storage. This balance between spatial resolution, image quality, and temporal resolution, motion fluidity, and storage capacity highlight the need for video compression technique. A video signal varies in both time and space, and this is represented by the formula F over X, Y, and T. In order to digitize the video, we need to do it in both space and time. For the space, each frame undergoes image is sampled and quantized similar in the way that we did for digital images. For the time, frames are captured at regular intervals, defined by the frame rate. Together, these processes enable us to represent motion while maintaining image quality. Storing and transmitting raw video requires immense storage and bandwidth. Early approaches like Motion JPEG treated the video as a series of independent frames, compressing each one separately. However, these didn't exploit temporal redundancy, which is the similarity between a consecutive frame, which is the novelty with respect to image compression and audio compression. Most natural videos have small changes between frames, which opens up opportunities for more efficient encoding. One of these techniques is called differential pulse code modulation, DPCM, that computes the pixel-by-pixel difference between consecutive frames. By storing only these differences, it is composed by a couple of steps. The first is that the first frame is stored like this, in full. Then the following frames are represented as their difference from the previous frame. Since consecutive frames are similar, these differences are usually very small, requiring fewer bits to encode them. We can see an example of an image created by the difference between two consecutive frames in a video. However, we can improve this method. In fact, in natural videos, many objects remain similar across frames, but move slightly. So this brings to a new method which is called motion compensated DPCM, also said MCDPCM, that accounts for this by detecting and compensating for object motion before applying DPCM. This results in having smaller differences between frames, further optimizing compression. The method MCDPCM forms the foundation of many modern video compression standards. Let's move to the conclusion. In this module, we explored how digital videos are created and compressed, highlighting the importance of frame rate, sampling, and techniques like DPCM and motion compensation. These methods enable the efficient storage and transmission of video content in everyday applications. Thank you for your attention.